The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Let me say just a few words of introduction of this international session. This international session ties with the convention theme, The Art of Concrete, and the title of this session, as you see, is Structural Concrete, an Art Form, and it is also related to the presentation I made at the international launch, and it will present the work of some eminent protagonists in the art of concrete, discussing at the end the problems that we face today about what is structural art today in the era of computer technology, in the era of virtual instruments. Who is the designer now? Who is the conceptor of a form? The terms of morphogenesis and so on will be discussed and introduced. We are in a new era where form may derive from the concept, but also may come in part from the virtual instrument of information technology, of information softwares, and so on. The first speaker is Maria Garlock. I am glad to introduce her. Maria Garlock received her bachelor degree from Lehigh University and a master degree from Cornell, and then she worked for Leslie Robertson Associates, designing some very important reinforced concrete building, including skyscraper. And then she returned to Lehigh to pursue her PhD degree, and then she became associate, as she is now associate professor at Princeton University. At Princeton, she cooperates also with Professor Billington. I am glad to introduce Maria, and she will speak about Felix Candela, structural artist. Please.
Thank you. Thank you for the introduction, and thank you for inviting me to be here as part of this session. Before I begin my presentation, I do want to acknowledge David Billington, who did the research with me on Felix Candela. So he and I co-authored a book together on Felix Candela, published in 2008, and we also put together an art museum exhibition on Felix Candela. So I'd like to acknowledge my colleague David Billington for his contributions for what I will present today. So before I begin discussing Candela, I will tell you that my perspective, or my point of view, what my research pointed to, I should say, about Candela is that really he was more of an engineer than an architect. So I'm guessing that those of you who have heard of Felix Candela have identified Candela as an architect. And what the research has shown is that in reality, if I were to use 3 words to describe Candela, it would be engineer, builder, and artist. And actually that's the subtitle of the book we wrote. I say artist, not architect, because then the confusion comes that you have to be an architect to be an artist. Now in the case of Candela, the confusion is understandable. He was actually trained as an architect. But if we study Candela's own words, his spoken words, his written words, he disassociates himself from being an architect. And he actually has said, quite literally, that he does not consider his work to be architecture. But of course, It depends on how we define that word architecture. And if we see these beautiful structures, they are structural forms, and they're beautiful structural forms. So there's the other confusion. When you see a beautiful structure, one automatically assumes that the designer is an architect. And in the case of Nervi, for example, we heard Nervi, or some of us did at lunch today, Nervi was an engineer, trained as an engineer, working as an engineer, yet he was an artist. So there's another example. Nervi is someone else that we would consider as structural artist. All right, so with that brief background and perspective of where I'm coming from, I'm going to start with an introduction to who he was. So Felix Candela was born in Madrid, and that is where he attended the School of Architecture in Madrid. And during this time, during his studies, he developed a strong interest in shell construction. So this is Eduardo Toroja's Zarzuela racetrack, the Hippodrome. It's still in existence today. These kinds of structures that were being built in Spain at the time by Toroja really inspired Candela. But shell design was not part of his formal education. And so what he would do is he would go to the library and copy by hand the papers that were mostly written by the Germans, Dischinger and Finsterwalder, copy the German by hand, copy the mathematics by hand, translate at home with a Spanish-German dictionary, the language, learn on his own the higher order mathematics. He was self-training himself to be this great shell builder that he eventually became. Now, after he finished his studies, this is the 1930s in Madrid, the Civil War broke out, and he ended up fighting in the war, went to a concentration camp, and in 1939 he was exiled to Mexico. And it's in Mexico that we see his important works be built. It would be 10 years after arriving in Mexico that he would start now experimenting with shells. And he would go back to this passion that he had about shells. So he would, now he had a little bit of money, he'd purchase the publication. So here we see in Candela's own handwriting in the notes, he's studying again these papers that he had in Spain written by hand. But he's also understanding that to become a shell builder, you can't just stop with knowing the theory. You have to practice it and understand the practical limitations of shell construction. So on the right, in 1949, we see his first shell construction of funicular form. And in 1950, he starts his own company, a company that would be dedicated to the construction of shells. Now, at first, he started with traditional shell forms, the single curvature, cylindrical barrel-type structures. But the geometric form that will become synonymous with Candela's name is the hyperbolic paraboloid, abbreviated HYPAR. So for the HYPAR, we have a double curvature surface. Double curvature has a tremendous more amount of stiffness than single curvature. So we see that the curvature comes in two directions like a saddle, and it can be generated with straight lines in two directions. So this is a huge advantage for construction because no longer did he need to use curved pieces of wood for the formwork of his shells. His first hyperbolic shell was the Cosmic Rays Laboratory at the University of Mexico City, UNAM. And for this project, the project director invited Candela to be the builder, the contractor. And already there was a project architect involved. And the architect asked Candela to build a single curvature wagon-like structure. And Candela went to the architect and said that he would instead like to build double curvature shells, two saddles back to back. And the reason for this was several reasons. One is that the shell at the very top could only be 5/8 of an inch thick. 5/8 because it needed to be able to measure the cosmic rays inside the laboratory. And Candela knew that the shell and therefore needed that double curvature for that stiffness. Later on, well, I should say as the shell goes down, it thickens to 1.5 inches. So all of Candela's shells are actually 1.5 inches thick. That's the dimension that Candela used to build his shells, and you can see that extreme thinness on the edge. He also took the ideas of the architect, modified the supports, again, another kind of aesthetic touch to the design, and also changed the screen. He corrugated the screen because Candela liked the way that the shadows played on that surface. So here's an example, and you'll see many more, of where there's an architect involved. Candela's hired as the builder, but the builder who makes the engineering calculations, he takes a general idea, which typically comes from an architect or somewhere else, and he modifies it to create his own art. Here we see that shell under construction where indeed we can see the straight lines, the straight wood that's used to generate this double curvature surface. Again, a geometric property of the hyper. Now for his company, what we call the bread and butter structure are the umbrella forms where we see the hyper shell up here. If we take 1/4 of that, you have this red dot here, copy it over 3 more times, we get this inverted umbrella structure. And we saw an example of umbrellas at lunch by Nervi. This is Candela's umbrella. And here's a sketch, a rendering made by Candela where we see that even the foundations below ground are umbrella forms, all hyper surfaces. And the idea here again came from somewhere else. So he saw this paper in 1936 written by a Frenchman named Imon. And Imon, this was a sketch that was in the paper, but we see again the touch of the artist. So they're both umbrella forms, both perfectly fine structurally, but look at the column, a short, fat column versus a tall, slender column. Look at the edges here. We have a very thick beam on the edge which thickens at the valley. A perfectly rational engineering design. However, he was able to make them nice and thin at the top. So again, the idea where he's taking an idea or a form from somewhere else and making his own art with that form. By placing many of these side to side, you get a large roof covering. So there were many warehouses and markets that were designed in Mexico. If you go to Mexico City, you're almost likely to run into one of these umbrella forms. And by tilting that umbrella, there's a light well in here that allows light to enter this huge covered space. In this example, not only does he tilt those umbrellas, but he pierces them with glass bricks to allow even more light to enter the space. And then here's a very playful way for this umbrella form where you can see he's pinching those umbrellas to create a very plastic, a very different way of designing these umbrella forms. This is actually just for a subway station, but you see even for a subway station, he doesn't compromise the elegance of his designs. And here's a closer view where if you look closely, you see the lines here indicating that he's using straight pieces of wood, again, that hyper surface, to form this concrete. And the biggest play of the umbrella is actually for this church, Our Lady of the Miraculous Metal Church. I call it Milagrosa. Milagrosa means miraculous in Spanish. And if you look at it, and if I didn't tell you, or if you didn't study Candela, I bet you wouldn't see the umbrella form in there. So the way that Candela explains how the form is derived is you take an asymmetric umbrella, shown on the left, and then you tip it so that this surface here is now touching the ground over there. And you take the center point here, lift it, you place another one back to back, and here you see on the right that image of that one bay of that church. So here is a tremendous play of this form, of the umbrella form. And one thing that we say about these structural artists, Candela and Maillard and Nervi, is that they are disciplined by efficiency and economy, and they play with the elegance. So there's many solutions to an engineering problem, so you just modify and you play with it to achieve that elegance. And that was really his ethos for how he approached his designs. So this structure here, again, he was hired as the builder. There was an architect that was hired for this design. The architect had in mind a hangar-like structure, just a cylindrical, one single curvature, like a hangar, airplane hangar structure. Candela again went to the architect and said, I'd rather not build what you've shown me, I'd rather build this. He had in mind this, and he'd been itching to design something similar to this. But this time the architect said no, but Candela is quite a persistent person as far as I can read, and he went right to the monks and convinced the monks to just build this instead of the architect's design. So again, being part of a project, but not the project architect. He was the project builder, but the builder who was making the calculations. And here's a view of it from the inside, where we see what he's doing. And he said he's essentially, this is a Gothic style for Candela, this ascending tendency. This was his redefinition of Gothic. And on the inside, you see these columns here, which are those columns of that umbrella that we remember tilted and leaned on its side. So you see a little bit of the umbrella form, but again, not very evident unless you study Candela that this is indeed a derivative of that umbrella structure. And also in all of his umbrella structures, he has drain pipes that run through the columns there, because if you look at the top, you imagine that the rain would fall and capture a lot of that water. So in some designs, the water runs through this pipe and it goes to a cistern where that water can then be used for irrigation. I'm showing this aerial view, and you can see this from the ground too, this thickening up here of the ridge. So as I said, his shells are 4 centimeters or 1.5 inches thick. At the top in this structure, there's a sculptured pattern increased to 14 centimeters. And you can see this from the ground as well as you walk. And if you're walking around the church and you see this, or even the aerial view, you see it's a very nice aesthetic touch to the structure. Imagine it plain. It would still look beautiful, but maybe not as elegant. There's this nice aesthetic detail. But it's not an aesthetic detail first. It's an aesthetic detail second. The first reason for that is an engineering reason. This was in the 1950s, the mid-1950s. He was making hand calculations and predicted that in this shell right here, if it would, assuming 4 centimeters all the way through, that shell would have too much tension, which would lead to a leaking roof. And he also calculated that if you can add some weight at the top here, add some weight at that ridge, that tension would disappear. So his way of adding weight was to increase the thickness of that concrete. And I'm not going to show you the results, but at Princeton we made finite element analyses, so these modern complex analyses. Candela did not have these tools in the 50s. And we indeed showed that his calculations were correct, that if that extra weight was not there at the top, there would be too much tension in that shell leading to cracking. However, adding that weight on the top does indeed reduce that tension. So his calculations that he made in the early 50s were indeed correct in the assumption. All right, so let's go back to the curved edge. So he begins with the cosmic rays, his first hypar. But the hyperbolic paraboloid can have curved edges, curved surfaces as shown here, or it can have straight edges. Right, so the umbrellas and the derivatives of umbrellas are examples of the straight edges. But he wanted to go back to the curved edges and find out how can he build these in a way that was didn't need to be continuously supported. So in this case here, this shell is continuously supported all along this platform edge here. And he was approached by some architects to design something different, something that would use curved edges but not have such a full continuous support. And the idea came to him, and the method of calculation also came to him to do this. So instead of having 2 saddles back to back, you have 2 saddles now intersecting each other. So imagine, take the saddle here, keep only the shaded region, cut out this blank region in here, intersect it with this one again, keeping only the shaded. And if you intersect it, you get this groin bolt shape. So he understood how to derive the geometric form and also how to make the calculations necessary to understand the stresses that would be in this structure. And the way that it works is really that the shell carries all of its load down to the valley or the groin, this area here. So all of the loads in the shell move down into this valley here, which is stiffened. So in that valley, he's thickening the concrete from 4 centimeters to 12, and there's a large amount of concrete in here where he's placing a lot of steel because it's really acting like a 3-hinged arch, those groin valleys, and he's understanding this. And by making it stiffer, it's attracting the forces. For restaurant Los Manantiales in Xochimilco, this is one of his masterpieces and actually one of his self-identified favorites. He's taking not 2 saddles and intersecting them, but he's taking 4. So to understand how this shape is derived and how, because I struggled with this when I started studying Candela, I'm looking at Los Manantiales and I'm saying, how in the world is that formed with straight lines? All you see is curves everywhere you look. So the best way to explain it is actually through an animation. And a few years ago, some graduate students made this animation where you start with a hyperbolic paraboloid sheet. All right, so this is a warped surface, and the straight line generators, in this case, are at 60 degrees to one another. So here we start off with one hypar sheet, and we're going to start cutting away at it. All right, so we cut that part out. And now what we're starting to see is two petals. This is what I call a petal here, two petals. And by cutting the edge here, what we see now are the parabolic edges. So you're starting to see this parabola here. That's this parabola there. And then you copy it over 3 more times. And you get the surface that you see for the shell on the left. All right, so now you can start to understand and see the advantages of this hyperbolic paraboloid, that you can use now straight pieces of wood to generate this very curvilinear surface. So if you look at it from the outside, again, 1.5 inches thick, you can see on the right just how very thin that structure is, and what a large scale. Here's some scale factors. And on the left, from high up, you see there's actually a little canal. I don't know how many of you have been to Las Manantiales. There's these canals you could take for a boat ride, and Mexicans like to party on those little boats. And it's a really fun place to visit and to be. This is a construction image where, again, you see that indeed he's using straight pieces of wood to make that formwork for the structure. So he has straight line generators in two directions, 60 degrees to one another. And here you see they're starting to lay out the steel. So he has 2 directions of steel, 3/8-inch steel bars also in the shell. Of course, for concrete, you need that for temperature and shrinkage and other effects of concrete. From the roof, you'll see patches of red, and that's because they used to have red waterproofing on it, and then it had white waterproofing. So you'll see some of this patching going on, but I've climbed all over the roof, and the roof is in excellent condition. Same with the inside. You look on the inside, I would say with relatively little maintenance. His Candela structures, I've visited several of them, are in good shape. 5 minutes? Okay. And again, you see the imprint of the formwork. Chapolomas de Cuernavaca, 1 single stretch saddle. Again, the straight line generators are evident. And if you look here at the lines, again, you see that imprint of the form, how this was built and constructed. All right, in 1954, Candela goes to MIT to a conference, and he learns about a collaboration between the architect, Minoru Yamasaki, and engineer Anton Tedesco for the St. Louis Airport Terminal. And this terminal, the vision of the architect was intersecting cylinders. Remember how Candela was doing intersecting hyperbolic paraboloids? Here we have intersecting cylinders, cylinders being single curvature. Recall, single curvature doesn't have as much stiffness as double curvature. Anton Tedesco told the architect, you can't build it like you want it. You have to have these stiffening ribs along the valley and on the edge. And of course, the architect didn't want this, but the engineer gave him no choice. And that is indeed how the terminal looks today. It has these stiffening ribs from the outside. It disguises now the thinness of the shell. The visual image is not anymore the architect's vision for the structure. And there was difficulty in all of that. And Candela knew, in listening to this, that the proper form and what would have solved a lot of the problems would to have been to make them hyperbolic paraboloids instead of cylinders. So he said that the next opportunity he had in Mexico, he would design or redesign the St. Louis Airport Terminal. So here's the St. Louis Airport Terminal, and in 1960 we see Candela's critique of the airport terminal in the Bacardi rum factory. So we see it is indeed the same structure, but not cylinders anymore. Now we have hyperbolic paraboloids. But not only that, he's taken these hyper shells and lifted them up with these little feet here, 2.5 meters higher. In 1970, 3 more shells were added to the structure. The other thing, by the way, he does have stiffeners, but the stiffeners are not at the edge. He pulls them back. So and the idea here is that he's able to express that thinness of the shell, one of the Candela's aesthetic. And here's to give you a sense of scale, 2.5 meters, he's lifting these vaults up higher. From the inside, on a cloudy day, you don't need any light, so it's flooded with natural light, and the people in there seem very happy to work in there, and I show an image of that to my students so they know to believe me that these factory workers are really enjoying working in this space. Yeah, I know, that's what they think, right? So, all right, so now I'm going to wrap it up. So I introduced Felix Candela as a structural artist. So the definition of structural artist is someone who designs efficiently. So designing for minimum materials, not using more materials than necessary, but of course still having the appropriate safety factors in your design. Next, he would have a builder's mentality. So the idea of you're designing something, but you also understand how it will be built, because a lot of the economy, especially for these shell structures, comes in the construction of them. And also that person will have an aesthetic intention. So the idea of there's many solutions to a design it to be elegant. So they are engineers, builders, and artists, as I said in the beginning, my definition of Felix Candela. And just to make clear the distinction between a structural artist and a master builder possesses the first two attributes. A structural artist includes that idea of aesthetic intention. And so what we see in this evolution of these structural artists, Felix Candela, Robert Maillard, and others, is they begin by imitating what they see and what they know. They innovate, and then they come to their final inspiration, their masterpieces. And I'll end with one quote from Candela, which wraps up this idea of art, concrete as art. He says, few people realize that the only way to be an artist in this difficult specialty of building is to be your own contractor. It may be shocking to think of a contractor as an artist, but it is indeed the only way to have in your hands the whole set of tools or instruments to perform the forgotten art of building, to produce works of art. Thank you.
Thank you very much, Maria. We have time for just one or two questions. We are a little out of time.
Again, it was a great presentation, as was the lunchtime talk that we had. One comment I just want to make is hyperbolic paraboloids are great shells. When I went to school, that was a long time ago, we didn't have the computers or the animation you showed. We also use this, by the way, in the soils to create a very, very inexpensive foundation, because all these forces are direct forces. There's no bending moment. That's why nothing of this sort will stand. I thought I'll just mention that. Thank you.
Thank you.
The young students should know all about that.
Yes, thank you. Actually, you're from India, you said, and there's a man named Sundaram in India who's building some beautiful shell structures, hyperbolic paraboloids as well. And he has mentioned he's inspired by Candela and his shells. Yes.
Maria, have you thought about why shells are not built anymore?
Yes, I have theories, but I can't say for sure. I think that the construction industry in the U.S. is very fragmented, and what Candela had, very similar to the quote I had at the end, is that he had control of all parts. So you have to be the engineer, you have to be the builder, you have to be the one creating the form and involved in all parts. It's very difficult to be the engineer and create a form and then pass it off to somebody else to build it for you. So that's part of it. It could be that, maybe academics like me or others who make the mathematics look so hard and scary sometimes, make it look like it's a very difficult thing to do. Maybe that turns some people off. It's very difficult to know, but in the 1970s, there was a decline in these kinds of structures. But I do know that it is possible to build them. Still, as I mentioned, in India, a man named Sundaram is building them, quite a few of them. He's probably the most prolific shell builder that I know of today, doing things. Another question I often get asked is 1.5 inches would never work in the U.S., but Heinz Isler in Switzerland is building them not 1.5, but I think 3 inches thick, or 2 or 3 times the thickness. Still a huge expression of thinness. I mean, that elegance of thinness is still there, so you don't need to do it at 1.5 inches anymore. 1.5 inches in the U.S. wouldn't meet code. You wouldn't get the right cover from the rebar, but it's still possible to do it today. You just have to have, I think, the proper people working on all of it.
Thank you, Maria.
Thank
again.
you.